Welcome, everyone. Thank you for joining us tonight for our stargazing lecture here at Caltech Astronomy. I'm Dr. Cameron Hummels. I'll be your host for this evening's event. So just a rough layout of how this is going to go. In a few brief moments, I'll introduce our speaker, who will give roughly a 30-minute presentation describing pretty awesome counterintuitive behavior around the vicinity of compact massive objects like black holes or neutron stars. And then following that, we'll take a brief Q&A with our speaker for a few questions, and then we'll kind of split, and there will be two concurrent activities that you can participate in. We'll have a Q&A panel here in this auditorium until about 9:45, consisting of our speaker, Nils, myself, and then two other members from the department. Some of whom work on black holes in other contexts, other than just the theoretical work that Nils is doing. And at the same time that we're addressing your questions, there will be telescopes set up on the fields directly behind me, which you can reach by going out the front doors, making a right turn, making another right turn. You can follow the primrose path out there. It takes about 90 seconds to get out there, so it's really close. And they're turning off the stadium lights tonight, which they haven't done in 6 years of doing this. So I'm really excited about that. So we won't be looking directly into headlights the whole time. And the conditions are really good tonight as well. As you probably saw, we've had all these atmospheric rivers flooding California, which of course is good for the drought and such, but it's been hard to do observational astronomy here in town. So finally we get some clear weather and we should have some really good views. Coincident with all of this, there's the media is kind of playing this up quite a bit, this planetary alignment that's going on over the course of the next week or so. It doesn't mean anything in particular. It just so happens that 5 or so planets and the moon are kind of on the same portion of the sky tonight and the next few nights. So already Jupiter and Mercury have set just after the sunset. But Venus is still very bright in the sky. Uranus is potential to see if you have a telescope or binoculars. Mars is visible and the moon is visible. So there's a lot of planetary objects to see, but there's also always deep sky objects like the Orion Nebula and the Andromeda Galaxy and the Pleiades star cluster. So lots of cool stuff to see tonight. These stargazing lectures occur one Friday a month. Our next one will be 3 weeks from tonight. It'll be a professor, kind of an esteemed professor, Richard Ellis, who used to be faculty here at Caltech. He's now at University College London, and he's coming back and going to talk about new first results from the James Webb Space Telescope, looking at galaxies on the other side of the universe when the universe was much younger. So that will be really cool. In addition, we have a sister series of events called Astronomy on Tap that take place at a bar restaurant in Old Town Pasadena, just a couple miles from here. Those consist of a couple of informal science talks given by scientists like myself or Nils. Nils gave one just a few months ago. And they also have live music. There's also telescope. There's astronomy themed pub trivia. It's pretty fun. Our next one of those will be 2.5 weeks from now. And we have some really exciting speakers. Both engineers from JPL, the NASA Jet Propulsion Laboratory, are going to speak. One is a woman named Shannon Statham, who is an engineer aerospace engineer who tries to make sure that the equipment that we send into space isn't going to break in the extreme conditions up there. And the other speaker will be the chief engineer of the entire Jet Propulsion Laboratory, a gentleman named Rob Manning, who is going to be talking about, he's basically overseen the program to land things on Mars the last 20 years, all the rovers that have landed there and such, he's been involved with, and he's going to talk about his experiences with that. So it should be really, really cool. I think those are all of my announcements. So I'd like to introduce our speaker for this evening. Nils Deppe joins us. He originally, he was born in Canada, in Manitoba. He went to University of Winnipeg for his undergraduate studies before he went and did his PhD at Cornell in Ithaca, New York. And following that, he came here, and he's been in the program as a postdoctoral researcher here for the last few years, doing some really interesting work in numerical relativity, making predictions about the behavior of space-time in the vicinity of black holes and merging black holes and what kind of gravitational waves come out from those sorts of objects. And he's been so successful in his work that he is being hired back as a professor at Cornell University starting this fall. So he's only here for a few more months before he returns and becomes an esteemed professor at Cornell. So please welcome Dr. Nils Deppe.
Thank you, Cameron. And thank you all for coming here. It being not Ithaca, but LA, I know you have a lot of options of what you could be doing tonight, and thank you for spending your time here. So I'm going to be talking about some maybe counterintuitive things and the sort of weird, wild, and wacky world of gravity, which on Earth is sort of boring, right? Apples fall from trees, you fall down, you hurt your knee, but what happens when things get a little bit crazier? So I'll be talking first about what are black holes, then spaghettification, I'll talk about what that is and basically what happens when you fall into a black hole. And finally, we'll talk a little bit about more of the sci-fi side of things and where does science end and where does sci-fi begin? So I'm a computational astrophysicist, which means I'm not an artist. I can do maybe grade 2 level art. So this here is my little cartoon character, Nilsy, and Nilsy's on Earth, not to scale, of course. And so Nilsy wants to go to space. All right, well, Nilsy doesn't know any billionaires, so how do you do this? It's a tough problem. Okay, well, it turns out if you want to get into space from Earth, you can jump, and if you're moving at 25,000 miles per hour, when you're leaving the surface of the Earth, you will just keep going forever. You will leave and go into space. So, you know, few leg days at the gym, some protein shakes, not a problem, right? So that's getting off Earth. And so then we also have the moon. And so let's say Nilsy got to the moon, either enough leg days or maybe Nilsy was able to make friends with some billionaire and now he's on the moon and he's like, cool, this is so awesome. But my friends and family are back home on Earth. My wife is upset that I'm not doing my chores around the house. How do I get back? To leave the moon, you need to jump at about 5,000 miles per hour. So maybe we don't even need the protein shakes, maybe just leg days, right? So then, okay, so 25,000 miles per hour to leave Earth, 5,000 miles per hour to leave the surface of the moon. Now we put Nilsy on the sun. We'll just ignore the fact that Nilsy would be burned alive and these kinds of minor details. That's fine. So in order to leave the surface of the sun, Nilsy needs to jump a little bit faster. It's 1.4 million miles per hour. So that's 1,400,000 miles per hour is how fast you need to go to leave the surface of the sun and never come back down. So then we can ask the question, okay, what happens if you have to move at the speed of light to leave some object, right? So we've talked about a moon, a planet, Earth, and the sun, which is a star. But what if we really said, okay, well, the speed of light is 671 million miles per hour. And what happens if you have to jump that fast to leave the object? And what you get is a black hole. And so the sort of definition of a black hole is it's an object in space where not even light can leave it. And so anything that wants to leave the black hole has to move faster than the speed of light. We currently don't know how to do that. And so that's why the black holes are black. You can't see them. We see things through light. So what if we wanted to take the Earth and turn it into a black hole? Nilsy's not very happy about this. This is, not really on his plan for the day, but so be it. So we create some giant sort of Earth compactor where we turn our crank and we squeeze it in. And so in order to take the entire Earth and turn it into a black hole, what you do is as you make the Earth smaller, you increase its gravitational pull at the surface. And you keep making it smaller and smaller, and eventually then the gravitational pull will get large enough that not even light can escape, and you have a black hole. And if you put your fists together, that's about the size of a black hole from the Earth. So if you turn the Earth into a black hole, it's about the size of your two fists together. So that's how much stuff goes into such a little black hole. So then you have this little object where not even light can escape. So if you've seen Interstellar, there's this planet called Miller's planet that's really close to a black hole. So here, this sort of black region, it looks better on a high definition laptop, but here it is. So this region back here, this is a black hole. And then what you have around it is a bunch of stuff, solar systems, stars, planets that are orbiting the black hole. One of those is named Miller's planet because some unfortunate soul whose last name was Miller got sent to it. And so what happens is that there's a bunch of astronauts far away on a spaceship, and they send a few of them to this Miller's planet. And time on Miller's planet is slower, going slower than it is further away. So this is one of these wacky gravity effects. Near these extreme objects like black holes, time actually runs slower. And so if you sort of do the math, or if you have a very mean professor that makes you do this for your exam during graduate school, you can calculate how slow is time going on Miller's planet, say compared to the Earth that's far away, and you get that 1 hour on Miller's planet is about 7 years. Right? So this gets really extreme the closer you get to the black hole. And so let's look at some clocks. We have a black hole. We have two clocks. And these clocks are orbiting this black hole. So you can think of this as, say, Miller's planet, and this as the spaceship. And so then as you sort of orbit around the black hole, you're moving, you're hanging out here, and you're looking at your watch, and you say, okay, 1 hour has passed. Your companions on the spaceship have aged 7 years. So by the time you make it back, they're going to be ready for retirement, probably. Right? And so this is something that actually happens. You can actually measure this. And this was measured in the 1950s at Harvard. They put two clocks, one at the bottom of a tower, the other at the top of a tower, and measured how quickly the clocks were ticking the seconds off. And this is, of course, on Earth, very, very small, but they were able to measure this difference in time, and it exactly agrees with what Einstein told us it should be. So this is actually a real effect. And it turns out that your GPS, right, like in your phone, in your car, everywhere, would be completely useless within a few hours if the people didn't take this into account. Because if your GPS tells you you're here or in the pool next door, that's a big difference, right? And so in order to keep this straight, you actually need to know exactly where everything is and how this change in the relative time of the different GPS satellites in your phone is affecting how you're locating yourself. So basically, gravity gives you this weird thing. It's called time dilation, because as you get to stronger regions of gravity, it's sort of time stretches out. And this is actually something we can even measure on Earth. And because of this, the core of the Earth is about 2.5 years younger than the surface of the Earth. And on Earth, it's not a crazy number, but you can actually measure this. So now what happens if you go into the black hole? So we've been going around it, now let's go into it. So we're going to go in feet first. It seems like the safe thing to do, right? Jumping head first is never a good idea if you don't know where you're going. And so what happens? What do we see? Yeah, friends, we're going in. Well, actually, nothing exciting. This is a really weird thing. I've been talking about all of this crazy gravity effects. And what you see is just the stars. You're just falling in, you just see the stars. You don't actually know when you cross into the black hole. There's nothing that tells you, oh, I've gone in. And let's say you're like, all right, well, my friend's back on the station, on the space station. I'm going to send them a message every 30 seconds just to check in so they know I'm okay. Well, as you're falling into the black hole, what actually happens is, remember that time runs more slowly for you. And so 30 seconds for you starts turning into hours, days, weeks, months, years, centuries. And so even your friends far away will never know exactly when you got into the black hole, because what happens if they get another message from you in 50,000 years? And so you have no way of knowing that you've actually ended up inside the black hole. And if your friends are watching you with their telescope, and let's say you have a nice blue spacesuit on, what actually happens is that as you fall in, you become redder. And this is effectively that the space is stretching out the wavelength of light, which makes it more red. And so while they can see you falling in, you turn redder and redder until you get into the infrared and even redder, and then they just can't see you anymore. But it's not because you're necessarily in the black hole, it's just because you're too red. That all sounds fine, right? Let's all go jump into a black hole. Seems great, no problems. Well, not quite. So what actually happens is that the gravity, I was saying, gets stronger as you get closer to the black hole, but the strength of the gravity also changes more rapidly as you get closer. So like the difference in gravity between your feet, this big arrow, versus your shoulders gets bigger and bigger as you get further and further into the black hole. So what this means is on Earth is actually that your shoulders are being pulled down less than your feet, but it's such a small amount that you don't notice this. But with the black hole, the gravitational pull is much stronger. And this is where you actually get turned into spaghetti. Your feet get pulled further down. Your shoulders are not being pulled as far. And well, most likely you would pop apart at the torso, but you get this sort of stretching effect going on. And this is what is fondly referred to as spaghettification. And so you're falling in, and eventually the gravitational pull on your feet exceeds that on your shoulders enough that you just get ripped apart. And then you say, okay, well, that sounds unpleasant. Sure. What happens to like my molecules, right? You're made of water. Well, those will eventually also get ripped apart. And then you say, okay, well, those are made of like protons and neutrons and electrons and stuff. What about those things? Those, as far as we know, will also get pulled apart. So basically what Einstein has told us is, as you go into a black hole, well, you can't really see anything happening. You'll certainly feel it at some point that things are becoming unpleasant. And those of you who are familiar with the Addams family, you basically, tie someone's feet down and start pulling on their arms, and you can sort of mimic this on Earth. Just don't, I didn't tell you to do this, but this is effectively what you get from this, is that you get this sort of stretching effect from your feet to your arms. So another very counterintuitive thing that happens, and sort of where Einstein came up with all of these ideas, is here I have Nils and a friend on two rockets, and they're flying at each other. Maybe not the wisest decision, but maybe they'll just miss each other. And so on Earth, if let's say you're on the back of a truck, a pickup truck, and you throw a ball, if you were, let's say you're a fairly decent baseball player, you throw the ball at 40 miles per hour, and the truck is moving at 40 miles per hour, then the ball will be moving at roughly 80 miles per hour. What's really weird is that with these two rockets, Nils measures the speed of light from his friend at 671 million miles per hour, the speed of light. And similarly, Nils' friend also measures Nils' light, the speed of light coming from Nils, as 671 million miles per hour. Regardless of how fast or not fast the rockets are going. And so this is sort of the key idea that Einstein had, is that the speed of light is always the same, regardless of how fast you or another object is going. This is sort of the key idea that really pushed us forward into this weird world of relativity and Einstein's theory of gravity. And so this is really sort of the underpinning idea that then culminates in these very weird effects, like the time slowing down, gravity becoming very strong. So that's all well and good. What about some more science fiction-y type things? So this is a spaceship. If you've seen Star Trek, the outline may look familiar to you. And so the question is, okay, well, what about Star Trek's warp drive? How realistic is this? Is this like completely science fiction? Could we get to something like that? What's happening? So the idea is you want to go from here to a distant galaxy or even a different solar system or a different star in our own galaxy. If you want to do this in sort of conventional means, it's going to take many, many generations. That is, you and a whole bunch of other people get on a spaceship, and then you will have kids, and they will have kids, and then maybe your great grandchildren somewhere down the line will get to some other star, and hopefully something interesting is there. If not, it's probably been a fairly long ride. And so the thing is, can we go to these things that are far away faster? And the challenge is, as I just said, is that the speed of light is always the same. And we can't even go at the speed of light, never mind faster than the speed of light. And some of the closest stars are many, many light years away, hundreds, thousands of light years if you want to go to somewhere interesting. And so that means what light years means is if you're traveling at the speed of light, it would take you, say, 1,000 years to get there. However, us as humans, we can't even get remotely close to traveling 671 million miles per hour. Like, I don't have any intuition for that. I find it a little bit spooky when everyone here on the highway is going 110 miles per hour, right? So what can we do? We can't travel this fast. So maybe there's some way we can cheat the system and get there. And so this idea actually first came out of Star Trek, this sort of warp drive thing. And they said, okay, well, there's this warp drive thing and you just go really far very fast, and it's like going faster than light. And then there's a physicist who said, okay, well, maybe we can actually do something like this, like theoretically. So they did a bunch of math, and what you can effectively do is you can cheat the system a little bit. So each one of these lines are sort of a measure of distance. This is sort of my standard measure of distance. We'll say they're 1 mile. And so what you can do is you can squeeze them together in front of you, make them larger behind you. And what this effectively does is it makes the distance from where you are to where you want to go shorter. You don't go any faster. You just don't have to go as far. And that's actually how you can make a warp drive. There's some big asterisks there we'll cover, but that is the fundamental idea of how you would make a warp drive. Is you sort of squeeze the distance, or you make it shorter ahead of you, and then you sort of make it larger behind you. And so this actually works. Like, Einstein's theory of gravity allows you to do this. And as far as we've been able to tell, Einstein is right. So at least theoretically, you can do this. All right, so before we get to the caveats, this is an apple. Credit goes to the apple tree that produced it. And then we can have a wormhole. So you probably can guess where this is going. And so the idea is you have a worm that chews its way through the apple and comes out the other side. And actually, the physicist John Wheeler at Princeton, he came up with the name based on actually holes made by worms in apples. And so what you can then say is, if I want to go from here to here, I have two ways of doing this. I can either go around the surface of the apple, or I can go through the worm's hole to the other side. And these will have different amount of distance that I have to travel, but they get me to the same place. So then the idea is, okay, well, maybe we can do this with space-time itself, our universe. And if you think of the universe as a big flat sheet that you then bend in half, and then the part you've bent in half, you connect through this tube then you have a wormhole. So this allows you then, if we have a point A down here and B up here, we'll say this is us, and this is some cool star that we want to go visit because we're going to mine the planets around there, whatever your favorite economically viable reason for doing this is, then you have two options of getting there. I can go the long way around, or I can go the short way around. And so the idea behind a wormhole, again, is that you can get to the same place, but you don't have to go as far as you used to have to go to get there. So you're not going faster than light, but you're not going as far. This all sounds too good to be true, and there are some caveats, and the big one is actually that this wormhole, it closes up. Gravity is pulling it together, so it wants to fall in on itself. And it actually collapses in faster than the speed of light, which means you can't get through here. So that's what makes it impractical to make a wormhole, is it closes up too quickly. And it closes up too quickly because of gravity, and gravity is pulling the things together. So then you can say, well, okay, what if we had something that rather than being attractive was gravitationally repulsive? So I have like a negative mass apple where if I let go of it, rather than falling down, it falls up. This sounds crazy, but this is if you step on the scale and it read -5 kilograms, that's what we're talking about. Things that have negative mass. We don't really know anything like this. We don't have anything like this, but that's what you would need, because that allows you then to get this pressure that holds open the wormhole. And you actually also need this negative mass stuff, whatever it might be, to make a warp drive work. So if we go back to our warp drive, right, you also need this to sort of expand the space, and then you can use matter to squeeze it in front. And so the key thing that we're missing is this negative mass stuff, whatever it might be. And so then you say, well, okay, that sounds kind of crazy. What are these people doing? And the answer is we can actually make things that weigh negative mass. We can do this. I kid you not. There was a physicist in the UK, Hendrik Casimir, who sort of predicted and told us how you would be able to do this. And then I think it was maybe in the 60s or 70s, people actually did this in a lab, and this space in here has negative mass. So you set up these two plates. Don't worry about all the squiggly lines, just ignore those. The important part is the space in between now weighs negative something, a very small amount. And the challenge is that, well, this is a very, very small amount of negative mass. That's all we can do right now. And in order to make a wormhole, depending on who you ask and who you're debating with, you get something around a few kilograms maybe, which is many millions of times more than what we can do right now. Or they might say, well, you need the entire mass of the universe, but the negative of that in order to hold a wormhole open. And if that's the case, I don't think we're ever going to get there. But in some sense, this is starting to move into, we can't say definitively that you cannot make a warp drive. We can't say definitively that you cannot make a wormhole. We just don't know how, practically speaking. And so there's some other ideas that have been floated around where, okay, maybe we don't need negative energy and we can still like create a warp drive. And it turns out you sort of can do that, but it's more like a railroad, right? So the issue with a railroad is you can't take the railroad to a new place because somebody needs to lay the railway lines and so get to that place first. And that's the same issue that you run into if you want positive or normal mass warp drives, is you now actually need effectively a railroad system that you have to build moving much less than the speed of light. And so if you want to build that to somewhere that's 1,000 light years away, this is going to take you probably many millions of years to build, because you have to slowly put all the pieces together, and all those pieces get put together by people moving less than the speed of light, and it just takes a very long time to build. And so, okay, we've talked about sort of warp drive and this kind of a thing, and you're sort of going faster than the speed of light, but not really, because you're kind of cheating the system. And so how does time travel come into all of this? And so hopefully I've convinced you that making a wormhole or making a warp drive is hard. It's not an easy feat to do. Time travel is significantly harder to do than that. So what is somewhat feasible is if you enter this wormhole and then place a black hole right near the wormhole, then that black hole slows down time for you. And what you can then effectively do is you can enter the wormhole at some age and leave the wormhole at the same age, right? So this isn't time travel as in backwards in time, but it is time travel as in you haven't aged, but you've gone somewhere. And so that falls into the realm of, well, if we can create a wormhole, we could probably figure out how to do this. Again, this is sort of in the same realm, but actually going back in time is nigh impossible. Also, you know, people have held parties for time travelers and nobody ever shows up. So it's maybe a good suggestion that it doesn't actually work out. But traveling backwards in time is really, really hard. And what's much easier to do, still not easy by any means, but easier to do, is to set up a time machine between A and B, and then you can instantly go between the two places. And so this is still time travel. It's just not time travel in the way we think of it, sort of usually in science fiction or this sort of realm where you go back in time and then like you kill your grandfather and then what happens? I don't know. It's sort of like, uh-oh, we broke our intuition of how things work. So the sort of punchline is gravity is really weird. It behaves very, very differently than what we're used to here on Earth. Once you start talking about things like black holes, these really dense objects where we've taken, for example, the Earth and turned it into a black hole and it becomes the size of our fists. The other thing is that falling into a black hole is kind of boring. Nothing really happens until you turn into spaghetti, and then it gets exciting. Finally, these warp drives and wormholes, they're technically possible. In some sense, we have the basic ingredients, and it's maybe you can sit, if you're very hand wavy, you could say, oh, now it's just an engineering problem. How do we make a huge amount of negative mass? And so while I'm not optimistic that we will get things like warp drives and wormholes in my lifetime, we also can't say definitively that it's impossible. So it's science fiction now, but we cannot guarantee you that it will always remain science fiction. Thank you. All right, so questions? Yes. Oh, yeah.
Thanks. So you said at the beginning that in order to jump off the surface of a black hole, theoretically, you'd have to go faster than the speed of light. But the speed of light is just a concept. That's the fastest thing we know, the fastest we know that anything can move. So is there a theoretical actual speed, call it, 1.5 times the speed of light, 2 times the speed of light, that would be the actual speed you'd have to jump? Now, I assume it would depend on the mass of the black hole. A larger mass black hole would require more speed to get out of its gravity. But the flip of that is there a minimum theoretical size mass that a black hole can be in order to have that work out to be, the speed of light plus 1 unit of whatever? Does that make sense?
Very good questions. So the first one is that the speed of light is always the same. So if you have a small black hole or a giant black hole, you need to go the same speed to leave its surface. And so this is sort of the fundamental idea that Einstein had, right? Is no matter where you are, what you're doing, the speed of light is 671 million miles per hour, period. So that is always fixed. And that's actually the key thing that sort of, with a bunch of math, results in time moving slower. Is the speed of light is fixed, so I can't change that, But if the speed of light needs to stay the same, I can change how quickly time changes. And so I have the same speed of light, but time is moving more slowly. It's not intuitive. You grind through the math and that's sort of what pops out. And so then you said, what about things moving faster than the speed of light? This is a great question. Things that have negative mass move faster than the speed of light. So that sort of gives you the sort of, oh, why would negative mass things work or could work? And it turns out that a weird thing from Einstein's theory of relativity is that you can have particles called tachyons is sort of the technical term for them. These are particles that move faster than the speed of light. They can never go at the speed of light. They have to always go faster than the speed of light. But other than that, they effectively behave the same as our universe does. They just can't ever interact with our universe. Right? So for all we know, there could be a bunch of tachyons everywhere. And if they don't interact with us gravitationally, then we have no way of ever knowing them because they also don't interact with us through the speed of light or through light. And so, speaking of difficult exam problems, my undergraduate professor was like, cool, we spent the entire semester learning that nothing can go faster than the speed of light. There are these things called tachyons. Rederive everything that you learned the entire semester for these things that move faster than the speed of light. And so we can't find these things really. We have no idea how we would find them, but mathematically, there's nothing sort of preventing them from existing. Yes. Right. Right. So specifically, can you have a small enough black hole that that things could escape? No. Right. So what if I understand correctly, what is the minimum mass of a black hole that could exist? And the answer is as far as tiny as you want, because the definition of a black hole is how little space the mass occupies. It's the density. It's the amount of mass per some volume that drives the gravitational pull. And so this is why, for example, the black hole at the center of our galaxies is huge. It's like, I think 1.4 million solar masses or something like this. It's huge, but it's only like the size of the sun. And so this is because what's important is how much mass you've crammed into a small enough space. That's what gives you the stronger gravitational pull. And so what you can do is theoretically any small black hole can exist. And now you can ask the question, okay, astrophysically, how could we actually, if we're looking out into the universe, what are the smallest black holes that we could possibly find? And there, the estimate is, between 3 and 5 times the mass of the sun, because basically if you have stars explode and they form what are called neutron stars, then the maximum mass of a neutron star, which is sort of the next densest thing to a black hole, is about 2.2 times the mass of the sun. And so that sort of gives you an astrophysical limit on how small of a black hole you could form in sort of the real world. But there's no small amount of mass that you couldn't cram into a small enough space to eventually form a black hole. You're welcome.
So I have a question, because you mentioned the theoretical model of the wormhole and then the black hole right next to it, which would theoretically allow you to time travel and come back to the present. But wouldn't that still violate the second law of thermodynamics, because entropy increases? So you wouldn't really be back to the present, right? I mean, there'd still be some.
Yeah, this is the other sort of crux with time travel, is that the second law of thermodynamics says that basically the amount of chaos in the universe increases, and what this basically means is that the universe eventually cools down, and stars, everything explodes and then cools down, and it's called the heat death of the universe. It's not a very pleasant thought, but this is another one of the central issues with time travel of like, there are other fundamental things in physics that we can test and show are right that then don't go hand in hand with what gravity tells us. And so this is sort of where you get into the realm of quantum gravity and how do you reconcile these differences of like small scale particle physics that we also can test and know works extremely well, but we don't know how to marry that with sort of these weird things that we get in gravity.
System in that theoretical model that you just mentioned, the wormhole and the black hole?
Yes. Yes, I don't know the technical answer off the top of my head. Sorry. Yeah.
We can take one more question before we pause and move to the Q&A panel and the stargazing.
Thank you for the talk. That was awesome. I was wondering, you had mentioned that the galaxies and planets and stuff are orbiting the black hole. And they're not, I mean, they're not getting, I wanted to verify that, are they getting absorbed at all? With like, given enough time, do they eventually get absorbed? Or what has happened? What are they feeling?
Yeah. So basically all of these things that orbit the black hole, they're moving at some speed. And so if you go on like playgrounds, I don't know if they allow this anymore. When I was a kid, you had like this ball attached to a pole and you could fling it around and it would keep going around. And you can do this with a tennis ball as well. So basically everything around here is moving at some speed. And so that's keeping it from immediately falling into the black hole. But instead it orbits and slowly its orbits shrink and they do eventually fall into the black hole. So this is very similar. It's the same thing as like satellites going around the Earth. They are effectively falling towards the Earth and the Earth keeps moving out of the way. And that's why they end up orbiting the Earth. But eventually that orbit starts shrinking and then everything falls in. And so this is sort of the eventual roughly end state of every galaxy is everything goes into the black hole. Bom, bom, bom. You're welcome.
It's a nice way to finish a presentation. Please thank Dr. Nils Deppe. Okay, so that's not the end of the night. We're also broadcasting this on YouTube. So if you saw some part of this, you were like, oh, I forgot exactly what he said. It'll be recorded. You can find our YouTube page and find this recording and like 100 other talks from the last few years that are on there. But so for tonight, what we're going to do is have like a brief intermission in here, taking about 5 minutes to just set up the table and get the rest of the panelists, who are we're all PhD astronomers, to answer questions from the audience about black holes, in case you didn't get a question asked, or some other aspect of astronomy or space physics that you're curious about. We can also take questions from our online audience. But simultaneously with that, we will have the telescopes are all set up. The lights are all off. They've got some great views for you. I encourage not everyone to rush off in a frenzy simultaneously, because then you're all just going to stand in line waiting to see the telescope. So it may behoove some of you to remain here and then go out later. But you're welcome to go back and forth between both the telescopes as well as here for about an hour until about 9:45. And just as a quick reminder, our next event, the next stargazing lecture, is 3 weeks from tonight on the search for cosmic dawn and first results from the James Webb Space Telescope, given by esteemed Professor Richard Ellis from the UK, from University College London. And then our next Astronomy on Tap is that week on Monday, April 10th, and it will be given by the chief engineer from NASA JPL, as well as another aerospace engineer who's also awesome, just not the chief engineer, who will be speaking at that. So thank you guys for joining us, and we'll transition over the next couple minutes to the panel Q&A. Thanks. All right. Thank you all for sticking around for our Q&A panel. What I think will be the most appropriate thing is I'll allow each of the panelists to introduce themselves, both by name as well as the kind of science that they work on, so that you have kind of some background on what our specialties are. I mean, we'll try and address whatever questions you may have, but everyone has specialties and is able to handle questions from particular areas more than others. So at least you'll know what our background is. I'm Dr. Cameron Hummels. I primarily do work in computational modeling of how galaxies form and evolve and change over very long periods inside of computer simulations that we can then kind of virtually observe and compare against observations taken with telescopes of real galaxies to better understand and interpret what we see through telescopes like the Hubble Space Telescope or the James Webb Space Telescope.
All right, so I'm Nils Deppe. I also do computer simulations, but I simulate black holes as they orbit and collide with one another, neutron stars as they orbit and collide with one another. And this, what we end up predicting are what are called gravitational waves. And we then give these predictions to people who make observations at the Laser Interferometer Gravitational Wave Observatory, or LIGO, because nobody can say the other one anytime. And so what they then are able to do is say, okay, we see some data, and then they match it to what Einstein predicted, which we get from computer simulations.
Hi, I'm Ed Nathan. I am an X-ray astronomer here, so I primarily look at accreting black holes, in particular looking at accreting stellar mass black holes, so kind of black holes the size, well, the mass of a few times the of our sun. An X-ray astronomer, so I also particularly look at X-rays which bounce off accretion disks back into our line of sight because they look quite fun.
So hi everyone, I'm Peter Borman. I'm actually Ed's office mate. I'm also an X-ray astronomer, but I'm very interested in the X-rays that are given off when supermassive black holes accrete material. It turns out that accreting material gets very hot and it emits radiation across the full electromagnetic spectrum. And I use the X-rays that are given off by detecting them with space satellites to be able to find out how many galaxies close to the Milky Way actually host a supermassive black hole that are eating material, but just behind lots of obscuring layers that we might not have known about previously.
Hi everyone, my name is Nivedita Mahesh, and I don't do black holes or study black holes. So Nils' talk today was very enlightening for me. On the other hand, I am a radio astronomer, so I use radio telescopes, which work very similar to our phones and FM. So I hate the phones and FMs when I do my observations. But I use radio waves to study how the very first stars of our universe form. We know a lot about star formation and of the nearby star. We know how they evolve and the properties of it, but we can't apply the same physics to our early stars. So we use radio waves to study the properties and their evolution. Yeah.
We've got the second mic. So there are a number of questions from our online audience, but I'll give you guys priority. If there are any questions here in the audience live, we can take one or two before jumping to the online audience. And I'll just pass the mic around to make sure not only other people here in the audience can hear, but also the online audience can hear the questions.
So in the experiment between the Casimir plates, what was the actual matter that became a negative mass?
Right. So what you end up with is actually negative energy, and the famous E equals mc squared tells you that energy is the same as mass. And so I fudged a little bit there. What you actually do is you make the vacuum energy negative, and that effectively then gives you negative energy, which is from a sort of black hole's perspective completely equivalent to negative mass. So it wasn't like, you know, negative applesauce or something like this.
Additional questions here? Yeah. And then I'll jump to some of the online questions.
Yeah, so a while ago, I started a project with some friends where we basically like kind of like map out the orbit for two binary planets orbiting a sun. And we started off with like a Newtonian approach, but then we kind of found that to be like a little bit elementary. So then we want to start working more with like Lagrangians and stuff. And we know that there's like Lagrangians that exist for like, you know, particles that, like under the influence of fields and everything. And like the Lagrangian densities and the actions are pretty easy to calculate from there with all the complex analysis. But then our problem is we don't want to pool the masses just because we want the whole idea to be like we have two separate entities that orbit each other while orbiting a sun. So then we're just having like a lot of trouble or working with the Lagrangians. We don't even know where to start actually. So we're wondering maybe if you have like any advice.
I can give you advice on the numerical side and how things might not go well. What you want to be careful is you want what's called a symplectic integrator to do the time integration. That's very important and something in these kinds of dynamics, and allows you to conserve energy, because if you don't conserve energy, I don't do planetary science, but you know, if you want to like evolve the entire solar system forward for a very long time, if you're not very careful and conserve the energy, you get completely wrong answers. In terms of setting up the Lagrangian, I can't do it on the board for you. I'm sorry. It's been a few years since I've had to do that. So when I have to teach it, I'll have to teach myself how to do it again. I don't know if anyone else happens to know the Lagrangian for these systems off the top of their head.
No.
So.
No.
The only thing I'll say is start off with the Newtonian Lagrangian. It's just a different way of formulating it. Start off there before considering relativity. It'll just make your life a bit easier.
Right. I guess so you can do a Lagrangian both in Newtonian gravity and in relativistic gravity. And the statement is stick to Newtonian gravity. Unless you have black holes, don't worry about the relativistic part. And if you have black holes, do a PhD, because solving those equations takes a long, long time and is not easy compared to the Newtonian case.
All right. Oh, well, I can't pass up this young lady's question.
So if there are black holes, do white holes exist too?
Okay, so white holes. Right, black holes, everything goes in. The idea is white holes is everything comes out. We haven't seen one, and you would think it would be very bright and white. Einstein's theory of gravity allows these to exist. There's sort of nothing preventing them from existing in sort of the opposite universe to where our black holes are. The sort of trouble I have with it is, okay, so there's all this stuff coming out. Where's it coming from? Think about that. If you can answer that one, then, but that's really the sort of trouble with it, is where does the stuff come from? And it would be super bright, and we would almost certainly see it in the sky. If anyone.
Agreed. There's a question. There's a lot of questions online, but one that kind of struck a chord was, are there any films or television programs that do that really nail the idea of a black hole, that do the physics justice? And similarly, are there television series or films that do it horribly and get it all wrong, and they're just an abomination in terms of the physics of black holes portrayed in the media?
I'll quickly talk about one that does it well.
Yeah, we've
Interstellar.
got one written by a physicist.
Yeah, so former professor here, Kip Thorne, was the science advisor on this.
He wrote the screenplay.
Yeah, and so most of the physics is right. The physics that even so, if you're like, it's a bit of a stretch, but it sort of mathematically works out. The image you see here is actually from Interstellar. It's mostly right, but it's not quite right. And this was intentional, because if you make it exactly right, it looks so weird that Christopher Nolan said, no one's going to believe that even in sci-fi. Right. So this is one that gets it extremely right, and they intentionally didn't do it as right as they could have because they were worried that people just wouldn't believe it.
So what did they intentionally mess up about it?
So one thing they intentionally ignored is that sort of you see how here around the brightness of this disk is very uniform. It turns out that one side versus the other is very, very different in brightness. I think I have an image handy that I can show later of what it really looks like. And then the other thing they did is here it looks, you see this looks fairly spherical. But in order to get a lot of the other physics right, this black hole needs to be spinning extremely quickly. And what that would actually do is squish it in a lot. And so rather than a sphere, it kind of looks like if you take like a foam ball, hold half of it, and then squish it like halfway in. So these are two things that they intentionally omitted when rendering this because they're like, nobody's going to believe this.
Wait, so the black hole shadow would be prolate? It would
be
like like an Easter egg?
Yes. Yeah.
Interesting.
It becomes very egg-shaped as you
I figured
increase
it'd
the
be
spin.
more oblate if it were rotating, like a hamburger instead of like an Easter egg. But
we can talk about frame dragging later if you want. But basically, as the black hole rotates, the things going away from you on one side are moving sort of faster than the things coming to, or moving slower than the things coming towards you. And so that actually the space-time warps. And so where the light moves around the black hole is actually changing just by the fact that the black hole is spinning.
You guys want to add any other films that that were awesome or horrible with respect to black hole physics?
So I think a film that doesn't quite get black hole physics right, but I do actually love it, is one of the latest remakes of Star Trek. So the one with Simon Pegg in the most recent one, where they essentially show a ship just coming directly out of a black hole with no problem, and they have matter that can produce black holes on tap. That's probably not the most accurate, I would say.
Yeah, just on the whole Star Trek thing. So I'm not going to be able to name any particular series or definitely not episode, but you definitely get this mind that, okay, there's a picture, the ship's in trouble, it's being pulled into a black hole and they're trying to get away from it. And like, it's just so nothing that they do can kind of pull them away. That generally, at least the way it's often portrayed of kind of like black holes sucking them in, is generally a bit of a misnomer or misconception. Until you get extraordinarily close, like close to the event horizon, the gravity from a black hole is mostly or pretty much exactly the same as from anything else. It's just a bit strong. It's not kind of like super sucking you in. You're just kind of falling in. The only problem is when you get really close and you have to be traveling at the speed of light to get away from it when you're that close to the event horizon, at which point, okay, maybe the warp drives are doing something a bit different. So a bit odd. But on a slight other thing, sorry, there was a series, The Lower Decks. It was a kind of animated version. I think it was on Amazon Prime. And actually in the title sequence, there is they visit what we call an X-ray binary. This is a stellar mass black hole and a star in orbit with each other. And okay, the ship does a bit of weird stuff around it. I'm not getting into that. But that's actually just the picture of that. It only flashes up for a few seconds. It's actually not too far wrong. At least it's a cartoon diagram. So worth seeing that if you watch.
Nivedita?
Actually, I had a question maybe for one of y'all. I'm just going to follow up. When you said things that went wrong in the Interstellar, was everything depicted at the Miller's planet made sense? What I have from memory is like, look like they struck.
Dilation?
Yeah.
Yeah. So on Miller's planet, the time dilation, it's exactly right. It's like I said, I had to do this on an exam, and it is exactly right. The other thing is you get these giant waves, right? On Miller's planet, they get whatever 11-kilometer waves or whatever. And if you do sort of a calculation too, they are exactly that height.
Oh, okay.
So the amount of time dilation matches exactly with the height of the waves. This turned out to be coincidence based on, Christopher Nolan and, whoever was doing the visual effects was like, that looks awesome. That's what we're going to do. And it turns out reality looks that awesome. And so, yeah, it's all of these, actually everything on Miller's planet basically checks out and is consistent with where it would be in orbit to get all of the same physics.
Thank you.
The films that I'd like to add that are not a good depiction of black holes. There's a film called The Black Hole by Disney from like, I think they'd really like to forget this film, to be honest. It's from like the late 1970s, early 1980s. It's weird. It's real weird. And I mean, to be fair, we understood a lot less about black holes 50 years ago than we do today. So you got to cut them some slack. The other film is a film called Event Horizon. That's a horror film from the mid 90s. And it's a weird movie. I went into it being like, oh, I like astronomy. And then I was like, yeah, it was unpleasant. It was, yeah, it's like a horror slasher movie, but they use a black hole as a warp drive in the interior of a starship, and science is a little not great. Yeah, another question here.
This is actually a corollary to this discussion. And if, as I suspect, no one will be familiar with this particular television show, I'll just ask a different question that I also have. But there was a recent adaptation, although that it's really loosely put adaptation of War of the Worlds. There was a joint production between British and French television. It really has very little to do with H.G. Wells' War of the Worlds, but it is inspired by that. And I, as Cameron can tell you, I'm desperate to talk about the show with people because no one else has watched it. There were 3 seasons there here on Epix. I assigned it to him months ago and he still hasn't watched it. But anyway, he has a life and I don't. So, but have particularly either of the Brits maybe seen this show? And if so, what would you say about the whole black hole thing going on in the 3rd season? Spoiler alert.
So I've already seen the first 2 seasons.
I have not seen it.
I haven't had a time yet to watch it, but yeah, indeed. There was another question from our online audience asking if it's possible to shear off part of an existing black hole to like create 2 or something like that. You didn't talk at all about Hawking radiation. That's a way that black holes can kind of evaporate, but is there a way to basically bisect one?
No. So basically, our current understanding of black holes is limited by we can't see what's inside of them. And so the current models are you have all of the matter going to the center of the black hole, like infinitely dense. This, of course, doesn't check out with like quantum mechanics or quantum physics. And so that the surface of the black hole isn't like a thing, really. It's a place in space where you can't escape anymore. But it's not like the surface of a planet where you could actually stand on it. It is still just space. There's nothing sort of special about it per se that you would like land on anything. So you can't cut a black hole or anything like that with at least our current understanding of them, given that we can't see inside of them. We don't really know exactly, but it's a good question.
I'm just reading over questions from our online audience, but are there any questions here? Yeah. Don't worry, online audience, we'll get to all of your questions.
With space is like there's galaxies, stars. I was wondering, when you guys study astronomy, how do you guys decide to study your emphasis on? How do you guys, from just studying astronomy yourself, when do you guys knew like, oh, I want to study this part of the space?
Yeah, when do we get a specialized?
So probably this is, yeah, basically when did you decide to study what you do, and how, I guess, sort of how did you get into this? You know how in life things kind of just like happen and all of a sudden you're there? Basically that. So for me in undergrad, I was taking a lab class I don't even remember exactly what it was on. And then one of the TA was like doing his PhD in black holes simulations. And I was like, hey, I like writing software. This sounds cool. And so I just did a summer research project with a professor. And it turns out that sort of I like the combination of weird physics, computational algorithms, and big supercomputers and writing software. That's how it happened for me, just sort of fell into it, I guess.
So I ended up going to astronomy because I went to university and I was studying physics. And going to university for me, one of the big fun things I wanted to learn was general relativity. I thought that was such a brilliant idea. It sounds so interesting. I read like popular science books about it, just I wanted to learn it. And I got about my third year of university. I was trying to like work out how can I make sure that this, which is normally like a kind of like final year kind of course, I can do it. Then I realized I made the wrong options and I hadn't done enough maths. Well, I'd done a lot, but not the quite right one to get me there. The only other way I could get there was to take some astronomy and just go into there. So I sat through some lectures on stars and planets, which like it was interesting enough, not necessarily what I was hoping for. And then some strange cosmology stuff and and then eventually general relativity. And having done all of this, I ended up just doing a summer project, given I wanted to do one. And actually, the more I got into it, I thought that actually all of this is really fun. So yeah, it's kind of like making the wrong choice and not doing enough maths.
So for me, I didn't start with astronomy. So I did a master's in particle physics. And bizarrely, I was actually studying micro black holes and how these can be produced when particles with enough energy collide together. Then they can produce micro black holes that then disintegrate with Hawking radiation, like Cameron was saying. And then when I was looking for PhDs, I spoke to someone in my astronomy group, and he actually saw that I'd done micro black holes, and he studied supermassive black holes, and he just said, oh, so you just want to scale up. And then, yeah, the rest is history, really.
Yeah. So being on the line of, I didn't start off with astronomy. So my undergrad is actually instrumentation engineering. So I'm an engineer turned astronomer. So I learned a lot about control systems and all of that. But then in my final year of undergrad, I had this research opportunity where I had to design an antenna for an astronomy project in an astronomy institute. And I was just there for a couple of months, like 6 or 7 months. And I attended a couple of astronomy lectures, got really interested. And there's something very romantic about the idea of, oh, I can study the very first stars of the universe while using my instrumentation and engineering background. So that's how I got into this. Yeah.
I studied computer science as an undergraduate but really enjoyed physics and astronomy, and later kind of melded the two when I went into graduate school. But yeah, I mean, the nice thing about this field is like, we're not entirely locked into what we do. Yes, we do work on these specific areas that we've chosen for the last few years, but people do reinvent themselves just as people do reinvent themselves in other parts of their life as well. So you could, get really excited about, some for stars or planets or exoplanets. Everybody's switching to exoplanets because that's a hot topic, to potentially find other worlds around other stars and potentially life there. So that's another area you can do. So you can always reinvent yourself. Don't feel too locked into what you're doing. Yes.
So what happens when neutron stars crash into each other?
What happens when neutron stars crash into each other? This is an exciting question.
Yeah, you tell me. Fireworks. So this is actually one of the big sort of open problems of in detail what happens. But basically, the neutron stars, as they get close enough, they start deforming each other, though. So they start as spheres and then they deform. And then as they collide, they fling out a bunch of matter. So you then have a single neutron star left after they collide and a bunch of matter around it. And this matter will then cool down very rapidly. And this is how you actually create things like gold, platinum, all these fancy metals that you like to turn into jewelry. And so this is one way that those form is through neutron star collisions. Then you have the center, this dense neutron star type object. And I say type object because I was saying earlier that the heaviest you can get for a neutron star is about 2.2 times the mass of the sun. But if the neutron star is spinning, then you can go above that because the rotation part actually holds it up and allows you to get heavier. And so these are then called supramassive neutron stars. And then you can change the way they're spinning and get what are called hypermassive neutron stars. And then eventually what they do is they sort of slow down their spinning. They slow down how fast they're spinning. And then they collapse into a black hole if they're above this 2.2-ish times the mass of the sun limit. And then you have a black hole with a bunch of really hot stuff around it that's cooling off and forming sort of cool materials, everything from hydrogen to gold, platinum, uranium, all these things.
Just want to add to that. So these are actually, we're beginning to look for these kinds of events, and we see them. Well, there's the gravitational wave events, which are being, I think, about last 5 years, 10 years?
1708,
Yeah. So, well, about 5, 6 years. So we've been looking for them. And alongside black hole mergers. The big difference, though, between a neutron star merger and a black hole merger is that, or a neutron star merging with a black hole, with two neutron stars, then they're not black holes. Stuff can escape, as you were saying, stuff flies out. So we see it. Can get really bright in the kilonova. Some of them, not mixing up my terminology here. So yeah, we do look for those, and I say we've seen one, I think.
Just one.
Just the one, yeah. I think there are other suspected neutron star mergers based on the masses, but yeah, I think we've only seen one. So yeah, there's a hunt on, can we see more? How common are these? A lot of the gravitational wave detections are black holes, which they're two objects where things can't.
But I think it's expected that, so the way that we detected that one that happened in 2017, as Ed mentioned, was this detector called LIGO, this instrument that can see gravitational waves, basically told us where in the sky. It detected something that was consistent with this. And then it said, hey, everyone, look at that portion of the sky. And so you had something like 25% of all the astronomers in the world got this secret message that was like, hey, point your telescopes at that section of the sky so we can see if there's some brightening or something going on. And this was about the same time as the solar eclipse that took place in 2017 that passed over the United States. Indeed. And so a lot of astronomers were like, couldn't participate in that because they were busy trying to observe this. I was not one of them. I'm a theorist. I don't control any telescopes except the ones out on that field. And so I was not contacted, sadly, to observe, but many of our colleagues were, and then saw this. But the reason I bring this up is because the LIGO gravitational wave observatory is turning back on. It's been off for a while as they upgrade the instruments and make it better. And it's turning back on in July.
Next
August?
month, every month. It keeps getting pushed back. Right now it's June, July. It was originally supposed to be March, but they've had some technical challenges.
And it will be on for a period of like a year.
It's about a year. Yeah. Yeah. And then both the Italian detector Virgo will be joining, and also there's a Japanese detector Kagra that will also be joining. And if you have 4 detectors, it's much easier to pinpoint where it is in the sky. If you have just one, you say, well, it's somewhere that we saw this thing from.
It's like if you have one ear and you hear a noise, you can't really localize where that is on the sky. But if you have 2 ears, you can be like, oh, that seems to be coming off in this direction. And if you have 3 ears or 4 ears, you can all of a sudden localize things very well to a particular location.
Yeah. Sometimes even the theorists get put on call.
Oh,
LIGO, yeah, they want follow-up simulations. If they don't know what they saw exactly, and they're like, we need you to run 200 simulations by next week. And you're like, well, we're going to have to ask the NSF for a bigger budget. Thanks.
Interesting. I didn't realize that.
Yeah.
So yeah, the hope is that when it turns back on, it'll potentially detect one of these neutron star mergers. And then astronomers, hopefully if there are 4 detectors, it'll have a much more localized location to search, and then astronomers will point their telescopes at that and potentially detect something like what happened in 2017.
They're expecting about 10 visible events
In the year
yeah,
of 04?
That's what they're hoping for.
Really?
As many as that, yeah.
That's exciting.
So we'll see.
So stay tuned.
We'll see or we won't see.
Stay tuned. Questions from our audience here in the back?
I'm having trouble imagining a collision of black holes that doesn't disintegrate the black holes. Like, if you took a deep sea, when you take a deep sea fish and you bring it to the surface and it disintegrates, and you have the supermass at the middle of a black hole, which is collapsing upon itself, when another black hole gets near it and it's actually, equalized in force, don't they just dissipate?
Black holes are weird. No, they don't. They do distort and they become sort of peanut shaped. But in this case, 1 + 1 = 1. So you have two black holes, they orbit each other. And then when they collide, you get one black hole afterwards that is initially sort of ringing like a bell. And then this is actually called ring down. It's the technical term for it. And it's sort of these deformations, or the sloshing goes away very rapidly. If you want, after, I can show you some animations from simulations of what this looks like. You can come down here and I can pull them up. We have them, our collaboration, the Simulating Extreme Spacetimes collaboration. We have a YouTube where we actually publish animations of some of our simulations. And so that's one I can show you after, but you can also look at them later if you want.
I have a question from our online audience. TY asks, if all objects in our galaxy eventually fall into the black hole, why do people say black holes don't suck? And how does it relate to the innermost stable circular orbit of a black hole? Because you during your presentation, you said eventually, kind of the heat death in the distant future, everything will end up present in black holes. And it is a common refrain. People will say black holes suck, and astronomers will say black holes don't suck. And essentially that the reason we say that is the conception that the public oftentimes has of black holes is that they're big vacuum cleaners, sucking up at anything that gets near. And in some respect they are, but not any more good at sucking things up than anything that has that same equivalent amount of mass. So the example that I like to use is if you take the sun and you just snap your fingers and instantly replace it by a black hole of the same mass as our sun is, the only thing that really changes in our solar system is that the lights go off. We continue on our orbit around that where that sun was, now being replaced by an equivalent mass black hole. We continue in our orbit around it simply because gravity is a product, or its higher end version of relativity, which is basically just gravity, is just a product of the masses of the objects. And the attractive force that you feel is a product of that. So as long as you're using a same mass black hole as to replace the sun, the gravitational effects should basically be the same. But given a long enough period, and I mean many, many, many times the age of the universe into the future, eventually you have enough time that the objects can undergo multi-body scattering against each other, and eventually things will either fall into the black hole or be ejected from the system entirely. And so that black hole will grow over time. And there are ways that it can evaporate, but those ways are much, much slower than the ways in which they grow.
So gravitational waves are actually one of the things that shrink the orbit. So even like a small planet, like even the Earth orbiting the sun, gives off gravitational waves. They just are so tiny that you can't measure it. And gravitational waves, as they leave, they take out energy from the system, and that shrinks the size of the orbit slowly over time.
But a very long time.
Very long time. Very, very long time. And so that's sort of one way that inevitably everything has to sort of plummet into a black hole, unless it gets this sort of, what Cameron was saying, this kick. from some other interaction where it then gets a lot of energy and flung out.
I just want to know every objects that orbit will give off these gravitational waves. They're not necessarily something specific to black holes. So like a planet rolling around the star will die long before this effect will happen, but in theory, the planet would also go towards the center. So that's not necessarily something like the black hole sucks in everything around it. It's just everything will eventually collapse down towards the center. And given there is a black hole there already, in pretty much every case, they'll fall into those.
More questions? Yeah.
I have trouble grasping the concept of time dilation. I mean, I sort of theoretically can conceive of it thinking of time as a theoretical dimension, but time is also a thing that we define. And so, and we typically think, we humans, not you people, we think of it in terms of our experience of time, seconds, minutes, hours, et cetera. So, and those are, and that's a defined unit. Like a second is, a certain number of oscillations of cesium ion or whatever. So, isotope. So when you talk about the experiment with the clocks, how, as a practical matter, do you measure that the time is running differently? Because, I mean, maybe I don't understand how clocks work, but my understanding is just there's a mechanism that humans have created inside clocks. I mean, I don't know if we're talking about atomic clocks, but although again, I don't know why it would make a difference. And that mechanism is created to tick off time at a specific rate. So why would gravity affect that?
Right. So before I get to that, one question you asked is like, how would you tell this? And so let's say you have two cesium atomic clocks that are synchronized here. You send one to the top of the tower, and then you let it sit there for a year. And then you bring it back down, and you look at, do they agree? And the result is that they don't agree. You get that one clock ticked a different number of times than the other clock. Like time literally. So you locally have your time defined, and this is a local definition for you. Like you have your time there, I have my time here, and if the gravitational pull is similar enough, we happen to agree. But if the gravitational pull differs, then gravity actually changes the relative change in time. So there's no absolute unit of time. It's a relative time. And so you were saying, in terms of like time, how we think of it, we're always moving forward in it. But let's say we're sort of like these otherworldly beings that can sort of look at it and say, okay, well, if I think of like just a line where you're moving from here to here and you have to move from the left to the right, then you can say, okay, well, you moved this way, but you can also move back. And so in this sense, it's just, you can define what the time is in the different regions locally, but you can also define it globally and then change the definition by sort of moving things around. And gravity, the weird thing about it is you can actually change the rate of time with it and how you define time. And so there's no unique one definition of what is time. And so what's actually changing is your definition of time versus the definition of time at the top of the clock. But you're both experiencing time locally in the same way. And so there is a somewhat sort of global notion of time you can impose on the universe. And you can then translate between the time at the top of the tower and the bottom of the tower. It's just that what your clock is ticking is actually different there.
So the standardized numbers in the SI unit of second is that at sea level or something? Or?
No, that's like wherever you are, that is how quickly the atoms decay. And it is a relative change. It is because you're in different locations with gravitational pull that time is ticking. Yeah, it's the comparison thing that makes that is the key thing there. So
it's definitely a counterintuitive.
Yes. Yeah. And the key thing is all of this falls out because the speed of light is the same. This was like the one insight that Einstein had. And from that, well, not the one insight he had, but this was like the key insight that all of this weirdness follows from that idea. That you can't change the speed of light, and so you have to change how time and space are behaving instead.
Do you guys want to add on that?
Yeah, I was just going to add that while this change is measurable, it's not really noticeable on a human scale, at least around Earth. But there is an important question, though, of humans need to agree. From all our systems to work, we generally didn't agree what the time is at any given time. So generally how I think that works is they've got these atomic clocks around the world. Okay, maybe they're all in slightly different conditions, but they've agreed on, okay, at least according to our measurement, our number, we'll just kind of average over them in some clever way. And it doesn't really matter that one's got out of sync. It's in a different gravity. We just go, okay, we'll choose that this one will be our number for now. So that's kind of, I think, how that's done. But
it's wild to me that scientists have to account for this effect with the GPS satellites that are to function correctly. The GPS satellites that are orbiting around us, because they're farther away from the Earth than we are here on the surface of the Earth, they have to account for time dilation. They also have to account for it based on the speed at which they're traveling, because special relativity, if the faster you're traveling, you get a similar time dilation effect that you would get by being close to a massive object like the Earth or like the sun or like a black hole. But it's like nanosecond different timescales, but you have to account for it or else it gives you the wrong results.
The gravity effect is fairly small, but the special relativity effect is actually huge. We're talking like 100 meters an hour is what your GPS would be off by. So like every hour you would be off by another 100 meters where you are on Earth. And that's
wild.
That's much big. I thought it'd be, like centimeters over a year, but no, it's like
significant.
On your bus drive to wherever you're going on your bus or your car, you're going to be going to the wrong place kind of thing. It's pretty crazy, actually.
That's why I still use paper maps.
Yeah, paper maps won't be affected.
That's true. You still might not know where you are on the map, but that's right. Yeah,
there was a question here specifically for Nivedita. You had mentioned that you were primarily studying the early universe using radio telescopes. Why radio telescopes and not the reference is, we know the James Webb Space Telescope is able to see kind of effectively farther into the distance, which effectively is earlier in the evolution of the universe. So why radio waves?
Oh, thank you for that question. And it's also a very good question. So one of the best things about radio is we probe an element that's present everywhere. So we look for a signature from hydrogen atom, and this is way before the very first stars and the galaxies formed. So we can study the universe much earlier, before the first stars turned on, since hydrogen was the very first atom that was abundant in our universe. So hydrogen has this characteristic signal that it emits at radio wavelengths, and it's exactly at 1.4 gigahertz. And if you try to probe the hydrogen from the early universe, which is way back in time, that signal gets stretched by the time it reaches that. So it goes even low in frequencies, let's say about 200 to 100 megahertz, which is where exactly your FM radio, if your favorite channel, if you think back to your favorite channel, it's very close to the same frequencies we are looking for the early universe hydrogen. So it helps us study the complete extent of the universe by looking at these signatures of hydrogen from the early universe, rather than looking at individual stars or galaxies that JWST might do based on, So we will look way back in time than JWST will, Did you all want to add to that?
Some more questions. Here's one.
To extend from that interstellar conversation from earlier, I have heard that I believe the Dr. Mann's planet, that the ice clouds were not scientifically accurate. If that's true, can you explain the physics of that?
Sure. So just to make sure everyone is familiar with what's being referenced, and again, spoilers, we're explaining much of the plot of Interstellar. Yeah, but exactly, it's several years old. So in the one of the final scenes, Matt Damon's character, Dr. Mann, is on a planet that's very icy. And in fact, when the spacecraft lands, it lands on a frozen cloud. They're walking around on this frozen cloud, and they talk about what the conditions are at the surface, which is somewhere below that frozen cloud. And so I believe this is the one aspect of the film that most people agree is not physically correct. And that is with the pressures, like we have clouds in our sky, and they're held aloft by the ambient pressure that we're, in the atmosphere that we're breathing and such. But to have a solid frozen structure up there would require an enormous amount of pressure underneath it that's supporting that to be kind of aloft. But for them to be in the conditions that they are, walking around and having low enough pressure that's present, it's just inconsistent. It would have to be much, much higher pressure and for those clouds to remain kind of frozen and aloft. So I believe that's the explanation for why the physics is kind of wrong in that scene. But do you guys have?
I don't know the answer, but if you're not aware, Kip Thorne actually wrote a book called The Science of Interstellar, where he goes through, I don't know if that specific case is in there, but most of the physics of like the wormhole and even like fun tidbits history-wise, how Carl Sagan, when he wrote a book, asked Kip, and Kip was like, these things are impossible back in the 80s. And then our understanding of black hole physics changed to the point where now some of the scenes that are present in Interstellar, Kip would not have been okay with back in the 80s. So I would highly recommend it. It's a very engaging and well-written book, and sort of is catered towards explaining which parts of the movie are sort of more sci-fi versus science fact.
That relates to another question that was asked online about, are there any books appropriate for kind of the lay person that handle the physics of black holes or general relativity particularly well that we could recommend? And so that might be, I haven't read that book, but I trust the fact that it's written by a Nobel laureate physicist, Kip Thorne, that it's probably pretty solid.
Yes.
But do you guys have other books that might be appropriate reading for the public level person on black holes or general relativity?
I found Stephen Hawking's books actually to be quite good and engaging and fun and
Sure.
Correct. Not maybe exactly what you're looking for, but a fun tidbit. There's a book called General Relativity for Babies or something like this that is actually very accurate, and it's sort of fun and is obviously aimed at little kids, but that's also just sort of a one that I would recommend, and it's fun and it sort of might be a nice gift for someone. If you guys have any other recommendations.
There's a book that I read many years ago called, I forget the exact title, but it was, the main character is a gentleman named Mr. Tompkins. These were written by another physicist, George Gamow, wrote these, I think, in the 60s or so. And they address some of these concepts of weird things like time dilation and length contraction and things that were referenced in Nils's talk. I don't think it specifically addresses black holes, but it deals really well with kind of a cartoon character walking along the streets on a bicycle, and he starts going very fast. The speed of light in that universe is much, much slower. And so he starts approaching that speed of light, which is like 40 miles an hour or something like that, and describes the different phenomena that he starts to appreciate, which we don't usually do because the speed of light is so much faster than the speed with which normal everyday things in our world travel. I found it very enlightening, as I think I was a middle school student when I read it. So that might be a good reference for people looking for some sort of intuition for how these things behave.
Yeah, unfortunately, I can't think of any books off the top of my head, although I've definitely read some before entering physics. But that reminded me of something I saw quite a few years ago now. And it was about a team It was at a university somewhere in the UK, I can't remember which one, who they created a little game. And the idea was like a small little world or a little map where you can walk around. And the object of the game is to collect about 100 dots that you had to walk around and get. I think it was, you can play either on a computer, which I think you can download, is out there somewhere. It also had a VR version. And the little trick was that each of these dots that you got artificially reduced the speed of light by a certain amount. So initially it's fine, just walking around, it looks normal. But then once you got a substantial amount of these and the speed of light is becoming to more appreciably human scales, you get to notice the kind of these relativistic effects. Particularly the first one that's obvious is actually like Doppler shifting. So when you walk towards things, they look bluer, and when things that you're walking away from look redder. And then you see other things around you like changing, they operate at a different speed compared to what you would expect because they exist at a different time. And there's not really so much, it's more special relativity than general relativity. But they were definitely developing this. And I think their goal, and I don't know how far they got with this, is to make it like a game. There's a whole like thing you can build, anyone can come and build a game with relativistic effects in, like a game engine. But they definitely made this one, and it's out there somewhere, I think, free for people to download and play with. Unfortunately, I can't remember what it's called. But.
All right. Right.
I have another question for the radio astronomer. Tried to ask a similar question last month, but nobody really had the expertise to answer it exactly. We've been emitting radio signals, techno signatures from Earth for over 100 years. And the question I was asking last month was, theoretically, if you were standing on like an exoplanet orbiting Proxima Centauri B with a radio, could you receive, would those signals sent 4 years ago, with it being 4 light years away, would they be audible, or would the signal, if you were, pointing in the direction of Earth, which is constantly, humanity is constantly sending out radio signatures at different wavelengths, would they be audible at that distance, or the signal so attenuated that they wouldn't be? And then like a related question is, could you listen to the radio on the moon, if that being closer and maybe would be less attenuated, like, with a time delay, obviously. Mm-hmm. Does that make sense?
Okay, so if I understand this, so if I am in Proxima Centauri emitting a radio signal, the other way around.
If you have a radio receiver,
yeah,
and the Earth is rotating and beaming out, radio signals are escaping from the Earth in all directions at all times, as thousands of radio stations around the world are emitting radio waves. That's 4 light years away. So if you had a signal, in theory, K-Earth is broadcasting right now, and let's say the signal goes out in the direction of Proxima Centauri B, and you're standing there with a radio 4 years from now, could you hear anything? And if the answer is no, because the signals are too attenuated, what about on the moon, where it's only 250,000 miles away?
So you're right about attenuation. One of the biggest thing about, so one, radios, it goes down by d squared, any of these flux, that is true. It'll be attenuated. I'm trying to think if our ionosphere, I was wondering if our plasma frequency of our ionosphere would also attenuate it. It's possible.
So
I want to say yes.
It's interesting that you asked this question, because there was a meeting taking place in this very room Monday through Wednesday about a new radio telescope that's being built in central Nevada called the DSA 2000 for Deep Synoptic Array 2000, because there will be 2,000 separate dishes. This is not going to be unlike, you guys are familiar with the Very Large Array, the VLA. It's featured in the movie Contact. It has those big radio dishes. Jodie Foster's famously wearing her headset, listening to the sound from these radio telescopes. This is going to be that similar scope. The dishes aren't quite as big. They're only 5 meters across, but there are 2,000 of them spread out over like 20 kilometers on a side. And one of the presentations was about technosignatures. So do we have the capability of detecting intelligent life around distant stars? And I think, so basically what Nivedita said is correct. But the challenge that we face is the attenuation. And if a foreign civilization light years away was beaming at us, specifically trying to get us to notice them by like shining their little flashlight of radio waves at us, yes, with this instrument and other similar instruments, if we were looking in the right frequency range at the right time, we would be able to detect them. But just to pick up kind of the ambient noise, like here on the Earth, you know, as you said, we have television signals, radio signals that are just going out. We're not directing them out, but they're just going out. We do not yet have the technological sensitivity to be able to pick those up from distant stars. But for the moon, yes.
Yeah. So actually, I'm glad you brought that up. So one of the couple of things that came up is when we see technosignatures, suppose there's someone emitting an alien civilization emitting a technosignature to us. One of the biggest thing that came up in the meeting was how do you tell that apart from something that's self-generated here? It might have similar properties. So how do you tell them apart from terrestrial things that we emit? And in terms of the moon, if the radio stations that we emit from here, we do see it on the moon. Now, one of our collaborators did do a simulations to see how much, if you go up to the moon, how much you actually see radio interference. Because the other thing that we at Caltech we're working on is building a radio telescope on the far side of the moon so that we absolutely do not see any emission from Earth. So it is picked up on the near side of the moon, some of the.
But if you're hiding on the other side, then potentially you're blocked from all the sound and the electromagnetic waves that are traveling off the surface of the Earth. Of course, until we start building things on the far side of the moon, and then it's a polluted radio space as well, which is probably what's going to happen, sadly.
Yeah, but with technosignatures, we'll have to do a lot of modeling to tell them apart from, is it from the alien civilization or is it us somewhere else we're picking it up from? Yeah.
Yeah. Yeah.
Let's see. You said earlier that we need to travel faster than the speed of light to escape a black hole. So it doesn't matter like the size of the black hole. Like what the supermassive black hole is the only thing different is like the size of it. Like is it just swallowing galaxies versus just swallowing planets, like the type of thing? So is that a big difference?
Yeah, one of the things is like black holes are sort of the simplest, most complicated things in the universe. They have a mass and a spin, and that's it. And the physics around them, no, they can, but not realistically. And so, yeah, it's the space around the black hole is the same whether you have a giant black hole or small black hole. Is just the distances at which you have to be from the black hole to feel the same amount of effect changes, right? But the sort of fundamental physics about like that time runs more slowly and that you need to move at the speed of light to escape, all of these things stay the same. It's just sort of, you know, your measure of how far away from the center of the black hole you are is of course affected by the mass of the black hole. So like how strong the gravity is depends on the size of the black hole, but the sort of underlying physics is the same. I don't know if anyone wants to add to that.
Yeah, I just add that, particularly in working things like everything, basically most of the units that we use in looking at black holes are generally scaled to the black hole mass. So we work in things called like gravitational radii, which is proportional to the mass of the black hole, and these kind of things. So actually, a lot of what we see, it's actually very difficult to work out the mass of the black hole. You have to kind of find a way to convert what we see measured in those units into kind of a physical unit, which is possible, but it's a bit harder. So.
Got a question in the back here.
Really quickly, in order for wormholes to exist, do we have to travel to the other destination?
Excellent question, and we don't really know because we don't know how to make them. So this is one of the problems, right? Is do you need to first get there to then connect it? How do you choose how you connect the 2 points? And this is one of these practical questions that we don't know the answer to, and would of course be a major concern, because if you want to get to other galaxies and you have to get there first to set up the wormhole, then we're still in the same sort of trap place that we are now. So we don't know exactly how you would get the 2 points connected. And that's, like, practically speaking, like you said, it's one of the biggest issues with making it happen. You're welcome.
So there's a question from online viewer Kiran Mehta, who asks, because gravitational waves can interfere, how can a black hole merger or collision be separated or isolated from gravitationals from kind of simultaneous events that are occurring at some other location, maybe more distant? In the same way, let's think about the analog of that. When you hear something from someone near, like a firecracker that goes off right here in this room close to us, how do you know that that's close to us and not, an enormous explosion that took place 100 meters away? How do we separate that out?
So right now we're sort of lucky that we only are detecting one signal at the time. Just the volume of the universe that we're able to probe with gravitational wave detectors on Earth means we only see one at a time. And that
we don't have good ears.
We don't have good enough ears
from nearby.
Right, exactly. And so, but this changes. This will change sort of as we get better detectors. So sort of the next generation of detectors on Earth, they will probably detect several thousand black holes a year. And at that point, the chances that two overlap becomes non-negligible. And the real challenge will be when we get a space-based detector, which is another one of these things that's a decade away every decade. It's a very challenging project, but at that point, you end up having hundreds of thousands of signals, what are called in-band, or there simultaneously. And so this becomes just incredibly challenging from the data analysis perspective. How do you pick apart all of these different signals? And you might have some loud signal that you can identify as the dominant signal. You can then remove the loud part from the signal, then do data analysis on what's left to pick out what's the next loudest thing. And you can sort of repeat this until you get to smaller and smaller scales. I'm not an expert on sort of picking out things, so I don't know if one of you guys are more into data analysis, but it's really the short answer is we don't know how we will do it for gravitational waves when we see a lot at the same time, but I assume you face similar problems in radio astronomy. So I don't know if you want to give a little spiel on how it's done there.
So for example, when we're doing the science of looking for the signal from the very first stars, right? So we look for radio frequencies. Now in radio, our own Milky Way is very loud, but we have observed it and we know how it looks. We model it out. So if you know the characteristics or the physics behind the brighter sources, you can model it out and then look for what's left behind. So I don't know if it'll be the similar thing we will do when you know the physics. Yeah.
So there's just another suggestion that the frequency of which these kind of the gravitational waves would be at, that is dependent on the masses that's going on. The properties that we see, although the frequency comes from the masses, which can also, I think, scale towards the amplitude, the size of these waves. So if you can get an idea of, well, we see these kind of frequencies, therefore we think that these kind of masses, so we expect them to produce this amplitude, and we actually see them at this amplitude, we can kind of begin at that point to start maybe work out that that's kind of distance towards the source. I think you probably actually know more about me, but
yeah, it's basically that you can measure the frequency and the amplitude at the same time, and the frequency tells you the masses effectively, and the amplitude tells you the distance to the source. So that's how you can find sort of the individual ones. And then when you have multiple, let's say if you have two and one is lower masses and the other is higher bigger, heavier black holes, then you would have sort of a big signal from the big black holes and then a small oscillation on top of this from the small black holes. And so that would be an easy case maybe where you could pick this apart. But then if you go from 2 to 1,000 or 10,000 things happening at the same time, it's an open question of how we are going to actually deal with this in practice, because it becomes modeling wise very challenging, because you have all of these things going on, and in comparison to the Milky Way, we don't know what the background is, because you have another black hole merger starting that starts to show up, and then then the other black holes merge, and so that signal disappears, and so you have these signals that are coming and going all the time that you then need to identify sort of on the fly. What are they all doing? And the real answer is we don't know yet how we're going to do it, and hopefully we have maybe 15 years to figure this out, and that's probably just enough time for us to get there. It's actually a very, very hard problem.
That's fair. Oh,
yeah, sure. So most of these events have you can look at follow-ups for these events in other wavelengths, right? So maybe we could use them to tell them apart. Like you can do radio follow-ups, you can do other wavelength follow-ups. Would they help?
Yeah, with the black hole detections, that's not really possible. Like if you get radio jets, but I think the chances of seeing jets from black holes, nobody's holding their breath that we will see any. So black holes, basically, if you have two black holes that have these sort of hot disks around them and they collide, then those disks, as they're being smashed together, would be very bright and you could possibly see them. People keep debating back and forth whether or not we will actually see this. Hopefully, like that'd be super cool, but it's not yet sort of theoretically understood whether practically speaking we would be able to detect that.
There's one more question from our online audience that I wanted to get to. There was a lot of talk about both gravitational waves as well as behavior around black holes, but what are the sort of electromagnetic signatures that black holes present in terms of how do we see them? There was some reference to radio, but yeah, how do we actually see these instead of just detect them through this kind of counterintuitive gravitational wave method and such?
Yeah, so it actually somewhat depends on the mass of the black hole. So for the typical sort of lower mass black holes that Ed was mentioning, the material that tends to spiral around tends to be smaller, because it's just a smaller disk, because it's around a smaller mass black hole, and because it's smaller, it tends to get hotter. And so that disk can actually heat up and emit X-rays, and you can actually detect with space telescopes, you can detect the X-rays that are emitted. But it turns out that if you're interested in supermassive black holes, they have a much bigger disk of material surrounding them. And because they're bigger, they're just cooler. And so that emits a lot of UV light and optical light, actually. And so that the primary signatures of an unobscured view to an accreting supermassive black hole is the majority of it comes out in the optical and the ultraviolet. Now, a lot of the material that's spiraling in that hasn't reached this hot disk of plasma, it just forms huge dense clouds that surround on much larger size scales. But these clouds are effectively just dust, and that dust heats up, and that heat is emitted as infrared light. And so the next biggest emitter that we can detect is with infrared telescopes, like the James Webb Space Telescope. And that's why JWST has already been very successful in finding lots of accreting supermassive black holes at extremely high redshift, because it's able to detect these packets of light that are essentially just reprocessed light. Just the same as if you were to look at a human with an infrared camera, you would see the heat, the warm-blooded nature of the human that's emitting that heat. It's exactly the same with an accreting supermassive black hole.
It's pretty interesting because, yeah, I think the more massive these systems, the higher the energy photons, but you're saying it's in some ways it's kind of the reverse.
Right. Yeah. Yeah. Exactly. For the primary radiation, and then the X-rays, which is the stuff that me and Ed primarily study, the X-rays are actually reprocessed optical and ultraviolet or X-ray light that's been reprocessed by like a cloud of electrons, whatever that may be. We still don't know. But it emits X-ray light that's just been reprocessed because these electrons are very energetic, and so they take the light that's being emitted from the disk of radiation surrounding the black hole, and they energize them and sort of shoot them up into X-rays, and that's when we see X-rays.
Wild.
Yes, I just want to add particularly to what I look at. So I look at these X-rays that people were just mentioning. Can actually hit the disk, and we see them again. And this imprints atomic features in. So if you just took a cloud of gas and you shine X-rays at it, you can get these atomic features, which are not quite, but these can be sort of like single lines. So certain energy, certain lines, which will then kind of fluoresce brightly. And if you look at a spectrum, you'll see like a line in that spectrum, very bright. However, when you got stuff very close to a black hole, it's moving very quickly. So, and different, if you get very close, it's moving even quicker. If you're a bit further out, it's still moving very quickly, but not quite as quick. And some of it's moving towards you, some of it's moving away from you. This means that every little patch of the disk has what we call a different Doppler shift. So that's the same effect as when an ambulance goes past, and when it's like going towards you or far away, it sounds different. It kind of changes that frequency or that energy. Are you about to show up a fun?
He's got a slide, an appropriate illustrative slide here.
Excellent. I'll wait for it.
Oh, that's the Doppler
There we
beaming.
go. So yeah, this is the effect. So what we'll see is the stuff coming over here, which is stuff moving towards you, is bright, but it's also what we call blue shifted. It's shifted to a higher energy. Or if you had like a white light, it would look a bit bluer. Stuff over there, it is red shifted. So it's a bit dimmer and it looks a bit redder. Stuff towards the black hole is actually also got some gravitational redshift on it. So when you get really close to the black hole, it begins to look a little bit red again. And the two effects kind of all weird on that side. Which means that when we look at it, and we don't ever see a black hole like this, when we look at a black hole, it's like a dot in the sky that we see in X-rays. But we can see these atomic features coming from across the entire disk at the same time. So rather than looking like a distinct line, we get this weird funky shape, which is normally double peaked because of two sides, with one side from over there at a higher energy and brighter, and then the side over there, which is just lower energy and dimmer. And putting all this all together, we can kind of use the shape of the line that we see. Yeah, I've done my pointing, but, but thank you. So we can kind of look at the shape. What does a single line actually look like to work out kind of how fast is the stuff moving, how close is it to the black hole, and kind of put all that together.
Excellent. All right, thank you, everyone. That brings us to the end of our evening. Hopefully you got something out of this. Online audience, hopefully you got something out of this as well. Did people get a chance to see stuff through the telescopes outside, and were the views pretty good? Cool, cool, excellent. All right, so thank you for joining us. Our next event, as I mentioned, 3 weeks from now, we will have our next lecture here, given by Professor Richard Ellis about James Webb Space Telescopes of the early universe, results of the early universe. And then that Monday, we will have Astronomy on Tap in Old Town, Pasadena with the chief engineer from JPL. All right, let's give a round of applause to our wonderful panelists. Thanks, guys. Have a good night, everyone.